Hello and welcome back to my channel. Today we're going to be talking about optimization. We talked a little bit about it last class, so now we want to look at some more problems. So a supermarket employee wants to construct an open-top box from a 14 by 30 piece of cardboard. To do this, the employee plans to cut out squares of equal size from the four corners, so the four sides can be bent upwards. What size should the squares be in order to create a box with the largest volume possible? So the first thing I'm going to do is draw this rectangle. So we need our piece of cardboard. And then we need to take out pieces from this cardboard. So what we're going to do is pull out a square from each corner. What this is going to do is if we were to fold up our sides here, so if I were to fold right here, right here, right here, and right here, and push these pieces upwards, it's going to create this box. So things that we know about our box, we have a side that is 14 inches and a side that is 30 inches. So volume is length times width times height, or base times height times depth. Length times width times depth, or base times height times depth. So we need to kind of figure this out. What we know is that we need to take a certain amount out of the corner. So what we're going to do is I'm going to label this amount that we take out of the corner as x. Because it is a square, the side of the square that we take out on both the length and the width is going to be the same. So if that's x, this is also x. So I know my depth, because this is the piece that's going to be folded upwards, is going to be x. So I already know we have times x. Our length, I'm going to make it this piece here, is the piece of the cardboard that's not cut out yet. So this piece in the middle, we know the whole thing is 30, but we're going to take out this piece and this piece. We are taking out the same amount from all four corners, so I know that this side is also going to be x. So the total is 30, and we're going to take away 2x's worth of those sides. On the other hand, we have this one right here. So the whole length of that side is 14. And we are taking away this and this. They are both x. So we're going to have 14 minus 2x. So this right here is our volume equation. It's in terms of one variable, x. Now we do everything we would normally do. So we're going to multiply all of this together. When I multiply this together, 30 minus 2x times 14 minus 2x times x is going to eventually get us 4x cubed minus 88x squared plus 420x. So we multiplied the two binomials in our parentheses and then multiplied everything by x. What we're going to do from here is this is the equation that we want to maximize. So this is the equation we need to take the derivative of. So v prime is equal to 12x cubed minus 176 not 12x cubed, 12x squared minus 176x plus 420. What we need to do now is set this equal to 0. One of the things looking at this is 176 is not divisible by 12, so we can't quite factor out a 12 from everything. We can factor a 4 out from everything. So we have 4 times 3x squared minus 44x plus 105. And then we're going to factor it. In order to multiply these together, I need something that multiplies to 3x squared, so a 3x times x. We have multiplying to get to a positive, adding to get to a negative, so I know they're both going to be negative. And then I multiply 3 times 105 to get 315, so I multiply it to 315, add to negative 44. That happens to be negative 35 and negative 9. 9 is the one that's divisible by 3. So I know that that's going to kind of pair off into this weird spot. So we're going to have x minus 35 and x minus 3. I'm going to set both of these equal to 0. So we get x is equal to 3 and x is equal to 35 over 3. So now we need to decide maximum, minimum, and things like that. When I look at this problem, we have 2 x values. So this is when kind of looking at which one's a maximum, which one's a minimum is kind of important. The other thing that we want to keep in mind is we're talking about a piece of paper. 35 over 3 is a little bit more than 11. It's almost 12. If we look at our problem, if I took out 12 inches from this side, that would leave 2 inches on this side, but then I couldn't take 12 inches on that side, so we would be cutting off the entirety of the width here, which means we can't cut out squares. So we know that based off of our problem, this isn't going to work for our domain. The biggest amount that I could possibly take out is really close to 7, but not quite 7. And really close to 0, but not quite 0. This tells me that 3 is probably going to be our value that we look at, but just for consistency, we're going to look at our endpoints. So the least that I could take out would be 0. So I could take out 0 inches. 3 was our critical point, and the most I could take out would be 7. If I take out 0, then I have 0 times some other stuff. If I take out 7, 14 minus 2 times 7 is 0. So now what I have left is figuring out what would happen if I plug in 3. So I have 30 minus 6, 14 minus 6, so 24 times 8 times 3, so 576, and this would be inches cubed. So I know for a fact 3 is going to be our maximum. So what size should the squares be in order to create a box with the largest possible volume? The square that would give the largest possible volume volume, not value. has a side length of 3 inches.